Alrighty, so what we are going to do today is a little bit different than what we've done previously. I have a problem from an old test that's pretty difficult. I would say more difficult than anything I would put on your exams now. This was from the first or second quarter I was teaching here at Tech, and was told by the other professors teaching the class that this problem was too hard. So we're going to work it today here, and I'm going to show you that it's really not all that hard. And it is a great example of learning how to apply nodal analysis techniques. So hopefully some of you guys watched the lecture. What is the first step that you should do when performing nodal analysis? Yeah, identify our nodes, all right? So we have this node, this node, this node, so that's 3, 4, and 5 nodes total. All right, so our nodes have been successfully identified. What is the next step that we should take? Define our reference node. All right, so which node do you guys want to use as our reference? Bottom. All right, seems fair. So to be our reference, it switched from the Ethernet cable somehow to the Wi-Fi, and that caused the connection to get lost for a moment. I don't know what the hell is going on. I've contacted IT. Let me jump back into the problem now. Alrighty, so this circuit contains voltage sources. Anytime we have a circuit that contains voltage sources, whether they are independent voltage sources or dependent voltage sources, a supernode is going to be formed between the two nodes that are connected to the terminals of the voltage sources. So in this case, we're going to have a supernode, let's call it AG. So that's between node A and ground, because there is a 6-volt source placed between nodes A and ground. Similarly, we're going to have a supernode CD, because there is a dependent voltage source placed between nodes C and D. And lastly, there is going to be a supernode DG between D and ground. So let me just be clear and call these ground, just because we might reach a point, not today, where we're going to have enough nodes to where there might actually be a node G. Okay, so that supernode, let's use this color. All of these 3 voltage sources are actually then connected, forming a super duper node, okay? And I know that's a dumb and terrible name, but it's what I've chosen to use. So our super duper node is going to be like this. So it actually takes up the overwhelming majority of the circuit. That may seem like it's bad news, but it's actually incredibly good news, okay? So this super duper node, as it were, contains the reference node, right? Or our ground node. Does anybody recall what we don't do when our supernodes contain the reference from the lecture, video lecture? So if the supernode contains the ground or reference node, there's something very specific that we should not do. Anybody watch the videos? All right, so if the supernode contains the reference, we do not write a Kirchhoff's current law equation for the supernode. Okay, we never, ever, ever write Kcl equations for the reference node. And since the supernode contains the reference, we will not write a Kcl equation. Instead, we will just have voltage relationships. Anytime there is a voltage source in a circuit and we are applying nodal analysis, we have to write a voltage relationship equation for each of those voltage sources. And I like to start off with those because they're the ones, in my opinion, that are easiest to forget about. So voltage relationships. So for supernode A and ground, and this is how we're going to write all of our voltage relationships, okay? We're going to start with whatever voltage the source tells us it's supplying. So for the supernode A to ground, what's the voltage source there? 6 volts. So we're going to say 6 volts is equal to the voltage, the nodal voltage present at the positive polarity terminal. What's that? VA minus the nodal voltage present at the negative polarity terminal. What's that? 0. So we can say then that 6 volts is equal to VA. That is our first voltage relationship equation. For our supernode containing our dependent source, what's the voltage supplied by the dependent source? The dependent source is the one that's a diamond. Sorry, what was that? So it'll be something is equal to VD minus VC. What's that something? How much voltage is being supplied? What does the symbol tell us? 3Vx. Lastly, we have supernode D to ground. So as Ms. Michaels, I think, said, it's a 2-volt source. What's our voltage relationship equation going to be? VD minus 0, which is just VD. All right, so we have 3 equations right there. Now, current law equation for this supernode. Again, I can't reiterate this enough, and I'm going to see probably a third of you guys do it anyway, even though I'm trying to beat it into your skulls. We never ever write a Kcl equation that contains our reference node. We need to write a Kcl equation for our other nodes, which in this case is simply node B. It's the only one we haven't done anything with yet. So for this Kirchhoff's current law equation, I want to be very explicit about what we are doing. Let me choose a copy of this one. So we are going to be adding together the currents that are leaving this node. So that means the current flowing left through the 2 kilo ohm resistor and down through the 4 kilo ohm resistor. And we are going to write our equations in terms of our nodal voltages. Okay, so let's start with the current directed to the left through the 2 kilo ohm resistor. Anybody have any idea how we might write that equation? VB minus VA divided by 2 kilo ohms. Thank you. Now, to be clear for any of you who didn't watch the video, what we do is we look at the node where the current starts from. So that's going to be positive. We subtract from that the node where the current ends up. So that's why it's VB minus VA. That's the voltage drop. And then we divide by the resistor value because voltage divided by resistance gives us current, just Ohm's law. So with that in mind, how are we going to define the current down through the 4 kilo ohm resistor in terms of our nodal voltages? VD minus VB over 4 kiloohms is equal to 0 because there's only 2 currents that can flow. That is our fourth equation, and we'll circle back around to it in a moment. Now, anytime we have a dependent source, we are going to have to define the controlling variable, which in this case is the voltage Vx, in terms of our nodal voltages. I want to be very, very explicit here because this is another place I see a lot of confusion about. I am not talking about the relationship that Ms. Shahara, is that correct? Said earlier that 3Vx is equal to Vd minus Vc, okay? I'm talking about we're dealing with this voltage Vx defined as the actual voltage drop Vx that is defined in the circuit, okay? We need to write an equation for that. Alrighty. So we said that the voltage relationship for Vx, again, was a voltage present at the positive polarity terminal of the 1 kilo ohm resistor, which was Va, minus the voltage present at the negative terminal, which is Vc, and this gives us a fifth equation. All right, so let's look at a couple of things here, right? Va is known, and Vd is also known. So I'm going to put green check marks by those guys, meaning we don't really need to do anything with those equations. It's very, very straightforward. Let's look at equation 4. Since we know Va and we know Vd, sorry, this is a mistake. This should be B minus D. Like so. We could say that VB minus 6 volts divided by 2 kiloohms plus VB minus 2 volts divided by 4 kiloohms is equal to 0, which we have one equation and one unknown. So could one of you please solve this for VB? Hey, I am very sorry. I do not know why the internet keeps dropping me here in IESB 112. I finished the problem for those students who were here in class, and I will just upload this PDF on Moodle for you all to see because I think we wound up, I'm not sure when the internet dropped out, but I believe it was at some point when we were writing one of our equations, but I'll put our solutions and all that kind of stuff up here for you guys to see. If you have any questions, I'd be happy to answer them. And again, I'm sincerely sorry. I don't know why the internet is freaking out in here.